Look at the data analysis and reasoning tier on this map. You have Agent 10, built to pull insights from raw data, and Agent 11, designed to verify those claims against trusted sources. They are highly effective, but they are narrow specialists. When a high-stakes question falls entirely outside their specific training distribution or predefined rule sets, those specialists hit a wall. They simply do not know how to handle the completely unknown. That is why we build Agent 12, the general problem solver. It acts as the cognitive fallback, a domain-agnostic generalist designed to take over when specialists fail. True system intelligence requires an architectural protocol for novel scenarios, a mechanism that can actually reason about its own reasoning. Imagine an electrical power grid plunging into darkness. A cascading failure spreads across the network, and traditional engineering models cannot adequately explain or stop it. To fix it, you might need to look at a rainforest. By borrowing structural survival patterns from ecology, specifically how food web modularity isolates the impact of a dying species, you can design a more resilient electrical grid. But building an autonomous AI capable of synthesizing knowledge across two fields as distant as biology and electrical engineering is difficult. Without strict guardrails, the language model will drift into unfocused hallucination. A massive context window isn't enough to bridge that gap. The system needs an architecture that actively evaluates its own reasoning strategy in real time. In 1957, researchers at RAND built a program called the General Problem Solver. It was the first computational attempt to separate the knowledge of a problem from the strategy used to solve it. It handled clean, symbolic logic puzzles perfectly, but the moment it faced the messy, unpredictable real world, it broke down. It was constrained by brittle, hard-coded rules. Today, we solve this problem with meta-reasoning. By using large language models as representational engines, the agent has the flexibility to connect abstract concepts and monitor its own thought process. The 1957 version guessed once and stopped. Our modern architecture watches itself fail, logs the specific deficiency, and tries again with a sharper approach. This diagram maps out the closed, self-correcting loop that makes this possible. It begins here at stage 1, decompose. Faced with a massive grid failure, the agent breaks the challenge into tractable subproblems. In stage 2, the agent conducts an analogy search. It hunts across diverse domains to find a structural match, linking the engineering problem to ecological food webs. It moves to stage 3 to synthesize and hypothesize. The agent stitches those borrowed ecological concepts together to formulate a new testable engineering solution. Stage 4 is where it tests and reflects. The agent stores its own hypothesis against a strict mathematical rubric. In our case study, the initial attempt fails, generating a low confidence score of 0.40. Instead of giving up, it hits stage 5, meta-learn and adapt. The agent logs the failure, generates a refinement hint noting that the first pass was too broad, and routes directly back to the start of the loop. On the second pass, the refined hypothesis scores a 0.78. That recursive loop, failing, reflecting, and iterating, is the structural mechanism that prevents hallucination and guarantees a defensible conclusion. Looking at this Python class, we see how that theoretical architecture translates into execution. The general problem solver starts by calling the decompose method to break down the initial prompt. Inside the iteration loop, it executes search analogies and generate hypotheses. These functions constrain the language model, forcing it to tackle one isolated step of the reasoning process at a time. The critical control flow happens at the confidence threshold. If the results score below the 70% limit, the script bypasses the return statement and triggers the refine and retry logic. Advanced AI engineering relies on deterministic routing structures that physically force language models to earn their conclusions through iteration. In a production environment, Agent 12 operates at the end of a trust-then-escalate pipeline. You use data analysis and validation agents to handle routine work and only escalate to the problem solver when a claim fails verification. Because this level of cognitive looping burns massive amounts of compute, this architecture is entirely inappropriate for routine, well-defined reporting tasks. It is also worth noting that fully autonomous meta-learning is still an active area of research. Currently, this system performs best with a human in the loop to set initial constraints and guide the decomposition. Even with those constraints, Agent 12 represents the shift from systems that merely retrieve static data to systems that actively construct new knowledge. This self-correcting cognitive engine lays the groundwork for what comes next. In our next episode, we apply these exact meta-reasoning mechanics directly to the task of writing production software with Agent 13. All the architectures and code discussed today are detailed in the sourcebook, 30 Agents Every AI Engineer Must Build. You can also find complete visual breakdowns on our website. Modern AI gains its power from an engineered willingness to be wrong, providing the space to reflect on failure and return with a smarter approach.